Beginning logarithmic functions. We just talked about inverse functions last unit, and we were introduced to logarithmic functions as the inverse of exponential functions. So that's going to be our first note on here, is that logarithmic functions are the inverse of exponential functions. Our more formal definition of what a logarithm is a logarithm is the exponent to which a specific base is raised to obtain a value. Okay, so logarithms are used to solve for exponents. I would like to start with graphing these two exponential functions, one's growth, one's decay, and then writing and graphing the inverse, which is going to be the logarithmic function. So let's just make a quick table here for y equals 2 to the power of x. Let's use -1, 0, 1, and 2. Gets us 1/2, 1, 2, and 4. So we'll go graph these points. 0, 1, 1, 2, and 2, 4. All right. There's our exponential function. Just last lesson, we learned how to switch our x and y and solve for the inverse. So we have x equals 2 to the power of y. And when y is in your exponent, we need to use logs to solve for those exponents. And we're going to go into more detail on this next class. But when you take the log base 2 of both sides, you can eliminate that base 2, and you're left with y equals the log of x with a base 2. And we'll write it in inverse notation. F -1 of x equals log of x base 2. And then if you remember, all of our inputs and outputs can just flip-flop. So now our inputs would be 1/2, 1, 2, and 4. Just flip-flopping these from our inverse function. So this would give us -1, 0, 1, and 2. And we'll go graph those points on the same graph. 1/2, -1, 1, 0, 2, 1, and 4, 2. Okay, so we have our inverse that looks like this. And that's what a logarithmic function looks like. There's another type of log function that has a base that's a fraction. So as you can see here, the base is 2. We can have a base that is a fraction greater than 0, less than 1. So why don't we do that over here? Let's just graph and write the inverse for this function so we can see both, okay? So again, we'll switch x and y. 2 to the power of y. Sorry, that would be 1/2 for this function. And then we would take log base 1/2 of both sides. And we get f -1 of x equals log of x with a base 1/2. Okay. Now to better understand what taking the log of something means, let's come back over here. Let's look at this function that we just graphed. If we know that the log of 2 gets us 1, this log expression is saying 2, because that's our base of our log, to what power gets us 2? We're plugging in 2 right here for x. And that answer would be 1. We are now plugging in 4, and this is saying 2 to what power gets us 4? Well, we know that that would be 2, and so on and so forth. So let's do the same thing over here, we always want, if our base is 1/2, we want powers of 2. So we definitely want to use 1. We can definitely use 2. And then 0 and 1/2 would be some good values as well. Or sorry, 0, yeah, 0 and, or I'm sorry, 1/2 and 1/4. We'll talk about why we can't use 0 a little bit later. Okay, we are asking ourselves the same question. We're plugging in this 1/4 right here for x. So this says 1/2 to what power gets us 1/4? Oh, that would be our 2, 1/2 squared. 1/2 to what power gets us 1/2? We're plugging this 1/2 now. That would be 1. 1/2 to what power gets us 1? We know that has to be 0. And then 1/2 to what power gets us 2? That would have to flip the base, so this would have to be -1. And we can go graph this 1/4 and 2 right here. 1/2, 1, 1, 0, 2, -1. So there's another example of a log function. Pretty similar to the one we graphed on the left. And I now want to talk about all of the properties of these two functions and see how they're related given that they are inverses. So our exponential function is y equals a times b to the power of x minus h plus k. Our log function form, pretty similar, y equals a times the log of x minus h plus k, with our base b down here. Let's come back to our exponential. Exponential functions, we have a horizontal asymptote. We have, it's always at y equals k. We have domain, that is always all real numbers. And then the range, which is usually everything above the asymptote. It can sometimes be everything below the asymptote if it's a negative a value. So then for a logarithmic function, we have a vertical asymptote. And hopefully you can, hopefully you can see that right here. Our vertical asymptote is the y-axis. Okay, and because the vertical asymptote comes from the graph being shifted left to right, the vertical asymptote would always be at x equals h. The h value shifts us left to right. Okay. Domain is now going to be different. The domain is going to be x is everything greater than h, or x is everything less than h, to the right of the asymptote or to the left. And range would be all real numbers. So hopefully you can see how these domain and range are related when they're the inverses of each other. They're just the opposite. And then same with horizontal and vertical asymptotes. All right, let's go graph these down below. Let's do some examples. And the way I'd like you to graph log functions is I'd like you to graph them in transformation form. Okay, I'd like you to know how to graph these. We can do these without a calculator. And when I mean transformational form, I mean, we're just going to graph the parent function. So for number 1, we're going to graph the function y equals log of x base 2. And we're going to make a nice little table here for that. For number 2, we're going to graph y equals log of x with a base 3. We'll take care of the x minus 1 beforehand. And then for number 3, log of x with a base, sorry, this is supposed to be a base 1/2. So we're getting a different type of example for all of these. 1/2, and here's our table. Okay. All right, let's do the first one together. We don't have any shifts left to right at all, so we know that our vertical asymptote is going to be the y-axis. And then again, you want to plug values in that are going to be powers of your base. So for 2, some good powers of 2 would be, well, definitely, we're always going to use 1, 2, 4, and then maybe we want to have 1/2 here. 1/2 would get us a negative value because, again, you're asking yourself 2 to what power gets us 1/2? Well, that would be -1. 2 to what power gets you 1? That would be 0. 2 to what power gets you 2? 1. And 2 to what power gets you 4? That would be 2. Great. We do need to account for one more thing, the -4 in front. Multiply all of the y's by -4. That's going to do 2 things. It's a vertical stretch of 4, and it's going to reflect us over the x-axis. So we have 4. This is still 0, -4, and -8. Graph these points. 1/2 and 4, 1, 0, 2, -4, and 4, -8. All the way down here. So this function looks like this. All right. Pretty steep because of that 4 in front. Just making sure I'm at the 8 units. And reflected over the x-axis. So normally a base 2 would look like this, but because we reflected over the x, it's now turning down, similar to what we had right here. All right. Why don't you try number 2 on your own? We just have, and then we'll do number 3 together. We just have one shift. This -1 in parentheses is a shift right 1. It's an h value. It's in parentheses. That's your new vertical asymptote. Plug some values in that are powers of 3 to your inputs, and we'll check your solution. All right, I would have used 1, 3, 9, and a third. A third, 3 to what power gets you a third? -1. 3 to what power gets you 1? 0. 3 to what power gets you 3? 1 and 2. So 1/3. And now that we've accounted for this shift, we're going to graph these points as if this were our new, right here, this were our new origin. This were our origin right here. So 1/3 -1 would be right here. 1, 0, 3, 1, and 9, 2. Gonna be a little bit off our graph, so let's just stop right there. All right, we got something like this. Great job. Let's finish up with 3 together. You have 2 shifts. You have a shift left 3, and you have a shift down 4. So this purple line, the vertical purple line, that's our vertical asymptote. And then I'm also going to graph this -4. It's not an asymptote, but I want to know where our new origin is. So I'm just going to move that right here. We're going to use this origin right here for a base of 1/2. And again, we want powers of 2. For 1/2, the only difference is you probably just want to use 1/2 and 1/4, more fractions. Let's put them in the correct order here. 1/2, 1/4. And then we always want to use 1, and another power of 1/2 would be 2. When we plug those in, 1/2 to what power gets us 1/4? That would be -2. 1/2 to what power gets us a half? 1. 1/2 to what power gets us 1, 0. And 1/2 to what power gets us 2, -1. So we're at 1/4, -2. Down here. A half, +1. Sorry about that. 1/2 would be +2. My apologies. 1/2 to what power gets us 1/4? That would be +2. Much better. 1/2 gets us 1. 1 gets us 0. And 2 gets you -1. If you wanted one more point on here, you could do 4. 1/2 to what power gets you 4? -2. And we have our graph. Graphing from the new origin. Okay, these are difficult. We haven't tried these before yet. Something you might want to make note of on here, you're going to see why, when we talk about these log expressions down below, you always want to use the log of 1, because the log of 1 and log of b base b. Okay, we're going to talk about y in a sec. You'll see these right down here. Log of b base b and log of 1. Before we do that, this is some good practice for how we use logs. They're used to solve for exponents. Sometimes you don't need logs. For example, 2 to what power gets you 8? We know that x needs to equal 3. Number 2 is asking the same thing. It's asking 3 to what power gets you 81. That's how we read this log expression. Log of 81 base 3. 3 to what power gets us 81? That would be 4. If you're unsure, we can just, in our calculator, 3 times 3 times 3, see how many times we get 81. Oh, shoot. So let's see how much we remember about 9 to what power gets us 3. It's not a negative because that's going to be a fraction. We talked about these right before winter break. We want the square root of 9, which means the exponent needs to be 1/2. And then finally for 4, we have a base that's a fraction. We want to flip that base and raise it by a power of 3, so that's why this would need, x would need to equal -3. The negative flips your base. 4 cubed is 64. Okay, here's what I wanted to focus on. Log of b base b and log of 1. These are really important because the log of something with the same base, it's always going to equal 1. Because this is asking 2/3 to what power gets you 2/3? Always going to equal 1. Similar, log of 1 base 5 is always going to equal 0. The log of 1 will always equal 0, no matter what the base is. Log of 1 base 1.3, 0. Because this is saying 1.3 to what power gets you 1. Anything to the power of 0 gets you 1. Log of 1 will always be 0. Last two properties, power property, and then, I'm sorry, I don't know why I put quotient property here. This should say common log property. Power property just states if we were taking the log of something raised to a power, a couple ways you could solve this. You could say the log of 16 squared. 16 squared is 256 base 4, and see what you get. That's going to be 4. But you could also take that power and move it in front and write this as 2 times the log of 16 base 4, and you get the same thing. So if you don't want to work with larger numbers, like 256, or maybe you're raising to something greater than a power of 2, you get the same thing because the log of 16 base 4, 4 to what power gets you 16? 2 also gets you 4. You could have also just taken this log expression, log of 16 base 4, and just raise it to a power of 2 as well. Both of those, all three of those would have worked. Okay, and then the last property on here, common log property, states if there is no base, if there's no base written, then you always assume that base equals 10. So the log of 1,000 is saying 10 to what power gets us 1,000. That would be 3. 10 times 10 get us 100. 10 times 10 times 10 would get us 1,000. Okay, great. The one last thing I want to finish with here, and then we're going to summarize those properties. When you have something like this, and we don't know what the answer is, well, here's where you have your calculator, and it will tell you exactly what the answer should be. We were working these earlier where if you just take the log base 2 of both sides, now you have the log of 2 base 2, and you can use this power property and move it in front. X times the log of 2 base 2 equals, you got to do the same to both sides. Can't do something to one side and not the other. Log of 2 base 2 is just 1, so we're left with x equals the log of 5 base 2. You would go into your calculator and punch that in on Desmo Scientific. I'll show you how to do that in class. And you would get x equals 2.32. Okay. You have to change a function on your calculator to do that. I will show you as well. All right, a brief summary. Log of b base b will always equal 1. The log of 1, no matter what the base is, will always equal 0. Power property, if we have the log of something to raise to a power, it's the same as writing this as that power multiplied by the log expression. And then your common log. If we have the log of something with no base written, we assume it's a log base 10. Okay. And I put one last thing on here. Going back and forth between the two if you ever want to convert. Remember, logs are used to solve for exponents. So if you have b to some power equals a, know that your exponent, when you rewrite it, would always go by itself. The log expression is used to solve for the exponent. So the log of a with the base b would get you x. And we'll use that throughout class. And you probably will on the homework as well. Okay, I know I threw a lot at you there. If the homework's a little confusing, we'll go over more problems in class. Remember, graphing, use the parent function. Use the parent function. Apply the transformations. You're asking yourself the base of that log to what power gets me my inputs, and then use your properties to help you simplify log expressions, and I'll answer any questions you have in class.